My dear students, a very good morning to all of you. Today we discuss another application of Gauss theorem. In previous video, we talk about how we can apply Gauss theorems. We study applying for Gauss theorem. We use 4 steps, and first first step is that consider a Gaussian surface. That Gaussian surface should be electric field and angle between electric field and area vector should be symmetrical. Second step is when we calculate E dot ds, and third step we find out charge inside the surface, and fourth is when applying Gauss theorem and we find out electric field due to continuous charge distributions. And we talk about previous video electric field due to a point charge and electric field due to a linear charge distributions. These two we already discussed. Today we talk about and we discuss electric field due to infinitely large plane sheet. First, let us suppose we have a large plane sheet which is infinitely let us suppose we have a infinitely plane sheet is, and this is infinitely large plane sheet, and charge are continuously distributed here. We find out electric field at a point P, which is r distance from this small surface. We consider a very small surface within the large plane sheet. How we can find out electric field at this point P? We use Gauss theorem and applying Gauss theorem. For applying Gauss theorem, we use 4 steps. First is when we consider a Gaussian surface. Which type of Gaussian surface should be imagined here so electric field and theta are similar, or we can say homogeneous. For this purpose we use a cylinder whose axis is normal to the sheet. Let us suppose we use a cylinder whose axis is normal to the sheet, and this is cylinder. This is cylinder. So let us suppose this distance is r, so also its distance should be r. That means why we use cylinder here, why we this type of Gaussian surface we imagine, because we know that Gaussian surface, we use that Gaussian surface where electric field and theta are symmetrical. Here for this, let us suppose we know that electric field is in this directions, electric field is in this directions, and electric field is in this direction. For here electric field is in this directions, electric field is in this direction. And for a very small, let us suppose we have a ds area, so areal vector is radially outward, area vector should in this direction, so electric field is in this direction and area vector also in this direction. Then angle between E and A will be 0 degree. For this is flat surface. Another flat surface we have, electric field is in this directions and a very small ds area, areal vector should be is in this direction, so we can say electric field vector and area vector both having in same directions, then angle between E and A will be 0. This is another flat surface. And we have a curved surface. This is curved surface. For this curved surface, electric field is in this directions, electric field is in this directions, so area vector should be is in this directions, so angle between electric field and areal vector is 90 degree for a curved surface. Then we use this type of Gaussian surface. The first step is complete. First step, always we consider a Gaussian surface, and here for a large plane sheet we consider a Gaussian surface in the shape of closed cylinder whose axis is normal to sheet of charge. P is on the surface, this point P, and this P is on the surface and extend equally on both sides. Second step, we calculate how much the flux linked to this Gaussian surface. So we have flux linked Gaussian surface is denoted by E dot ds, and E dot ds we separating, or we can say we cut this cylinder in three parts. First is one curved part, another is one flat part, and this flat part, two flat surfaces, or we can imagine this is one flat surface and another flat surface is this. So we have two flat surfaces. E dot ds for curved surface, we know that E ds cos of theta, theta is equal to 90, since electric field is in this directions horizontally and area vector should be vertical, then angle between E and A will be 90 degree, so cos 90. For this flat surface, electric field and area vector both having same direction, in same directions, then theta will be 0. And another flat surface, angle between electric field and area vector should be 0 degree, so E ds cos of 0. For cos 90 we know that 0, and electric field is same everywhere. Why electric field is everywhere same? Here this sheet is very large plane sheet, infinitely, so this electric field lines like as brush, or we can say toothbrush bristles, like as we see bristles are parallel to each other. And let us suppose this is, we have a plane sheet and charge are continuously distributed here. This is infinitely large sheet, so electric field due to here will be is in this direction. But if it is not infinitely large, it is not infinitely large, then we see electric field lines, electric field lines, electric field lines are, electric field intensity is different. How? Here is in this direction, is in this direction, but we see for this corner electric field lines are in this directions, electric field lines are in this direction, electric field lines are in this directions, and for this corner electric field lines are in this direction and electric field line are in this direction. Whenever we find out electric field intensity, we assuming a ring. It is similar, and here will be electric field intensity. The electric field line are passes through this ring. So 1 2 3 4, that is 4 is electric field intensity, and same size ring we consider here, so electric field intensity is similar for here. But if we take is in this direction, whenever we have large plane sheet is not infinitely, this plane sheet is not infinitely, then we take a ring here, so electric field intensity is some here, but on the in this corner electric field intensity is different from this positions, so electric field everywhere is not equal. for a for not infinitely large plane sheet. If we have infinitely large plane sheet is not. Now we here E dot ds and E dot ds. This ds, let us suppose here we have a very small surface, that is ds, and so ds we consider, and now then we integrate. Let us suppose this total surface area is s and this total surface area is s. So we have es plus es, that is equal to 2 es plus es is equal to 2 es. Now third steps is we find out charge inside the Gaussian surface. How much the charge inside the Gaussian surface? We find out charge inside this Gaussian surface. Here will be no charge, here will be no charge for only that surface. For we find out that charge which is inside the Gaussian surface. So we already take sigma. Sigma is surface charge density, that means charge in per unit area. Charge in per unit area is sigma, and this area we take s. So we have total charge inside this Gaussian surface is sigma into s. So we have total charge is equal to q is equal to sigma into s. Now last step we applying Gauss theorem. We already find out E dot ds and charge inside the surface. So putting all these values in this format, so we have 2es is equal to sigma s upon epsilon naught. Can s and s both are cancel out, and we have E is equal to sigma upon 2 epsilon naught. This is very important and versatile formula for us. Why it is important? So this formula is independent from r, and r is distance between this point to this point. So here distance is not matter. Whatever electric field intensity here and another positions, all where electric field intensity will be same. It is not depends on the r. We study in previous lectures electric field intensity due to a point charge is depend on the distance, but here we have a continuous charge distributions. That is point, that is understanding. So for a continuous charge distributions, electric field depends upon r or not depends upon r for a charge continuous, for a distribution is whenever continuous. So that is the formula for us. E is equal to sigma upon epsilon naught, and special conditions for this infinitely large plane sheet. We assuming a sheet, we have a sheet is always two surfaces, not a single surface, very thin. Whenever we take sheet, that means sheet having two surface, like as this is sheet, this is sheet, and here we have positive charges, and here will be a positive charges separate out. But if we take one sheet, that means one sheet, never we say about very thin. For a thick sheet we use two surfaces. One is this surface and another one is this surface. Sigma upon 2 epsilon naught is electric field intensity at this point due to this surface, and electric field intensity at this point E is equal to let us suppose this is E1 and this is E2, that is equal to sigma upon 2 epsilon naught. So if sigma is, then net electric field is equal to sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So total we have sigma upon epsilon naught for a thick sheet. This is expression for electric field. E is equal to sigma upon epsilon naught. Sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So we have E is equal to sigma upon epsilon naught. And another we have special conditions for this large plane sheet infinite. For infinite large plane sheet we have, let us suppose we have charge is, whenever two cases are here, similar charges and opposite charges. We have a sheet here positive charges and there here also positive charges, because we find out for a similar charges. One sheet is positively charged, so electric field at out left of one sheet is E1 is equal to let us suppose surface charge density is here sigma 1 and surface charge density here is sigma 2. For this sheet, due to this sheet, E is equal to sigma 1 upon 2 epsilon naught, and due to this sheet at this point E2 is equal to sigma upon 2 epsilon naught. Both having minus. Why minus? Minus we take here, since electric field is in this direction, and we know that when we consider a number line on the left hand side we have minus sign, so we take out E is equal to minus sigma 1 upon 2 epsilon, that is E1, and E2 is equal to minus sigma 2 upon 2 epsilon naught. So total E is equal to we adding both of them we get minus 1 upon 2 epsilon naught sigma 1 plus sigma 2. But if sigma 1 is equal to sigma 2, then we have sigma is equal to minus sigma upon epsilon naught. That is very simple. This is mathematics. But now we find out within the surface, inside the surface, we find out electric field intensity at inside. Due to this charge, electric field is in this direction, and due to this charge, electric field is in this direction at this point. So electric field having one we take out positive and another we take out minus. So due to this charge, E1 is equal to sigma 1 upon 2 epsilon naught, and due to this charge, E2 is equal to minus sigma 2 upon 2 epsilon naught. So we have E is equal to 1 upon 2 epsilon naught sigma 1 minus sigma 2. If sigma 1 is equal to sigma 2, then we have E is equal to 0. Third, we find out electric field intensity at outright at this point. Due to this sheet, electric field is here, E1 is equal to sigma 1 upon 2 epsilon naught. Due to this, E2 is equal to sigma 2 upon 2 epsilon naught. So we can say both having in same direction, we take out in positive directions. Due to these are on the right side, so net electric field we have E is equal to 1 upon 2 epsilon naught sigma 1 plus sigma 2. If sigma 1 is equal to sigma 2, then we have E is equal to sigma upon epsilon naught. This is expression for similar charges. But if we have opposite charges, then one sheet is positive and another we have negative. So we find out electric field at out left at this point due to this sheet and due to this sheet. So we take E1 is equal to minus sigma 1 upon 2 epsilon naught, because this is in this directions and number line in left side is negative, and but here is negative charge. So electric field lines is in this direction. That is important, because we know that electric field lines towards to the negative charge. So E net is equal to sigma 1 plus sigma 2. One is negative and another one is positive, so we can write as sigma 2 minus sigma 1. So we have E net is equal to 1 upon 2 epsilon naught sigma 2 minus sigma 1. If sigma 1 is equal to sigma 2, then E net is equal to 0. Within the surface, similar, we can find out within the surface at this point, due to this, E1 is equal to sigma 1 upon 2 epsilon naught. Due to this, E2 is equal to sigma 2 upon epsilon naught, and both are positive, so we have E is equal to 1 upon 2 epsilon naught sigma 1 plus sigma 2. And if sigma 1 is equal to sigma 2, then we take sigma, so we have E is equal to sigma upon epsilon naught. Another one we have at outright, if we take a right side, then at this point E1 is equal to sigma 1 upon 2 epsilon naught. Due to this negative charges, E2 is equal to minus sigma 2 upon epsilon. Why minus sign we take? Because electric field lines is in this direction, so this is, we take negative, so we have E net is equal to sigma 1 upon 2 epsilon naught. This is due to positive this, and E2 is equal to minus sigma 2 upon 2 epsilon naught. So net electric field we have E1 plus E2, that is equal to sigma 1 upon 2 epsilon naught taking common, and sigma 1 minus sigma 2. If sigma 1 is equal to sigma 2, then net is 0. So what we observe in these special conditions, whenever similar charges plate we have, then we always point out within the plate net electric field will be 0, but we have opposite charges. Whenever we have opposite charges, then electric field is some values inside, but outside both of side will be 0 when surface charge density are similar. It is very useful when we study about capacitor, then we use this thing and we discuss in that video. Thank you.